penetrate the heavily contested airspace over the Middle East, the bone sweeps those massive wings all the way back, locking them into the 67.5-degree combat configuration. This mechanical transition, aren't swing wings the best, transforms the aircraft from a high-lift heavy hauler into a sleek, swept-wing supersonic dart capable of flying Mach 1.25 at high altitude. Now, this speed is critical for managing the distance to threat aircraft and quickly achieving high dash speeds into hostile territory. The bone has a true party trick that terrifies adversaries and gave the Soviets absolute nightmares. It can fly on the deck, racing at Mach 0.92, just hundreds of feet above the ground, using the terrain to mask its radar signature from surface-to-air missiles. This introduces a massive and terrifying engineering mystery. If an aerospace designer takes an aircraft that is 146 feet long, which by the way is literally longer than a Boeing 737, and flies it at nearly the speed of sound through the dense, turbulent air at extremely low altitude, well, the aerodynamic forces would violently bend and flex the fuselage. And these intense vibrations could literally shake the airframe apart, and the crew would be physically incapacitated by the punishing ride. So how does the bone survive this brutal structural environment? Well, the answer is an absolute masterpiece of engineering genius. You see, engineers solved this problem with something called Structural Mode Control System, or SMCS. If you look closely near the nose of the Rockwell B-1B, you'll notice small triangular fins, but they aren't canards for steering. Instead, sensors detect turbulence and structural flexing, and these vanes automatically move in milliseconds, working with the lower rudder to cancel dangerous vibrations. Think of this as a hyperactive suspension system for a jet, smoothing the ride and protecting the massive fuselage so the bone can fly in flight regimes that would tear other bombers apart.